Okay, welcome you all once again in this series of lectures on metric spaces. In the last lecture, we have discussed the boundary point of a set in a metric space. So, again, I am repeating the definition. So, a point x in a metric space X is called a boundary point of a set A if it is neither an interior point of A nor the interior point of complement of A. In other words, a point X is a boundary point of A if every open sphere centered on X intersects both A and its complement. And the boundary, the set of all boundary points is called boundary of A, and it is denoted by in this way. And we have seen several examples and properties, and today we will be discussing several exercises on boundary of a set. So first let us see, here is first exercise. So suppose if you have A is a non-empty subset of a metric space X, then the complement of interior of A must the complement of interior of A be equal to the closure of complement. So whether this is equal to this thing or not. So this you can give the answer by producing an example. So here is you can consider, as I am mentioning all the time, first you try to consider the set of all real numbers with the usual metric space, and the second thing is that you can consider the discrete metric space. Okay. So here is to show that whether the complement of interior of A is equal to the closure of complement of the closure of A, it is true or not. So for that we consider the set Q of rational numbers as a subset of R, and R is equipped with the usual metric. And then we have seen that the interior of Q is equal to your empty set. Okay. And now, so if we are considering A is equal to Q, and then the interior of A is equal to empty set, and therefore the complement of empty set is equal to whole space R. So this is equal to your R. Now let us calculate this one. So for this one, the closure of rational numbers is equal to R. We have seen it before. And then the complement of this, so the complement of this is equal to empty set, and then you take the closure. So the closure of empty set is empty set, so this is equal to empty set. So here is we are getting this is equal to your R, but this is equal to your empty set. So this cannot be equal to this one. Okay. So here we have, it is not necessary that this is equal to this thing. Okay. Then we have several, you can see I have mentioned several properties of the boundary of a set in the form of exercise, and these are similar as we have done for the interior of a set or the closure of a set. So let us take X be a metric space equipped with the metric D, and A be a subset of X. Then the boundary of A is same as the boundary of the closure of A. Okay. The second is the boundary of A is same as the boundary of the complement of A, which is equal to the closure of A intersection the closure of the complement of A. This we have already given in the previous, just after the definition. And the boundary of A is equal to the complement of, so you take the closure of A, okay, and minus interior of A. That is to say, you remove the interior of A from the closure of A, you will get the boundary of A, which is equal to the closure of the complement of A minus the closure, interior of the complement of A. And here you can also prove that the complement of boundary of A is equal to interior of A union the complement of the interior of complement of A. And A must be equal to interior of A union boundary of A. So this we have seen. Similarly, the closure of A is equal to A union boundary of A. Interior of A is equal to B, okay, and you remove the boundary of A, that is your interior of A. So this you get it from here and here, and A is closed if and only if boundary of A is a subset of A. A is open if and only if boundary of A and A are the intersection have no point. Okay, so this you can prove very easily, and I am not going to prove all these things, but I can have another exercise which says that prove that any closed subset A of a metric space X is a countable intersection of open sets. It's a very important result, exercise, which says that any closed set of a metric space is a countable intersection of open sets. Okay? Keep in mind, arbitrary union of open set is open, and the finite intersection of open set is open. But here we are taking the countable intersection of open sets. So let us see here is for each natural number n, we can define ON is equal to the union of open balls with center at X and radius 1 over n. Okay, so for each n we can define the open balls. So this is equal for all X in A. So this we can, then you can see that because this is your open ball. Okay, this is your open sphere with center at X and radius 1 over n. And we have seen that open ball is an open set, and this is arbitrary union of open set. So we have already seen that the arbitrary union of open set is open, and therefore ON is open. Okay, and not only this, because at each point of A we are having an open ball and we are taking the interior. It means that the A must be a subset of ON for all natural number n. And therefore, you can see that A is a subset of ON for each n. So A must be a subset of the intersection of all ON, and intersection is table all natural numbers. Okay, and now we claim that OA is nothing but equal to this intersection. So suppose that it means that we have to prove that this is a subset of this one. So let us prove that, so to prove that this is a subset of A, then we can prove that this is equal to this. It means that A is the arbitrary the countable intersection of open sets. Okay, so now suppose that this is not true. That is to say, the arbitrary intersection of open set need not be a subset of A. So we assume contrary that there is a y element in this set, but it is not this in A. So this y is in the intersection of O(n) but not in A. And now since A is closed, the complement of A is open. Okay, so this is the complement of A and it contains y. Okay, because a y is not in A, so y must be in the complement of A. So this must contain y. Hence, there exists a epsilon positive such that the open ball, so this is an open set and contains O. So it means that this is the interior point of the complement of A. So there exists an epsilon positive such that the open ball with center y and radius epsilon must be a subset of complement of A. And now since epsilon is greater than 0, there exists a natural number n such that 1 over n is less than epsilon. Okay. Now since y is in On, because it is from here, y is in On for each n, there exists x in A such that dx y is less than 1 over n, and 1 over n we are choosing is less than epsilon. So this is less than epsilon. It means that the ball with center at y and radius epsilon and with the intersection A is non-empty. It means what? It means that y is what? Means that y is the limit point. Y is y. So that this is not empty. And now you can see that this implies that the A intersection complement of A is non-empty, and this is the contradiction. And therefore, what we are assuming that this is the subset of this, this is not a subset of this is not true, and therefore both are equal, and so this can be written. So any closed set can be written as a countable intersection of open sets. Now here are several other exercises. So the first exercise, again we have let A be a non-empty subset of a metric space X, then prove or give the answer of the following statement. The boundary of A is a closed set. Okay. So how we will prove the boundary of A is a closed set? Now we know that the boundary of A is equal to the closure of A intersection the closure of the complement of A. Okay, so both sets are closed sets and the intersection of two closed sets is closed. So this set is closed, this set is closed. So boundary of A is closed, and so this is proved. Okay. The second statement is that the boundary of A is same as the boundary of complement of A. Okay, so let us take first, suppose X is a boundary point of A. X is boundary point of A, then X is the center of X, for X is the center of an open sphere for any radius r is greater than 0. Okay, and then you can see that the ball SRX intersection A is non-empty, and this open sphere, because this is the boundary point, so any open sphere with center at X must intersect with A and its complement. So this is non-empty and this is also non-empty. But we know that the A is equal to complement of A and its whole complement. So we also have the ball with intersection the complement of A. Instead of A we can write in this way, and of course again is this way, and therefore this implies that X is in the boundary of complement of A. And by reversing the argument we will see that X belongs to the boundary of A if X is an element of the boundary of the complement of A. So this can be proved in this way. For the third one, that the boundary of A is equal to the closure of A minus interior of A. That is to say, boundary of A is equal to, you can take the closure of A and remove the interior points. So here is, so let X be a boundary point of A. Okay, so X is a boundary point of A if and only if every open sphere centered on X contains point of A but not a subset of A. Okay, and therefore the boundary of A is equal to the closure of A minus interior of A, as X is in interior of A if and only if it is the center of some open sphere contained in A, and X in the closure of A if and only if every open sphere centered on X intersects A. And this way we can prove the part, this C statement. Now the statement D is that if X is the boundary point of A, does X have to be a limit point? In other words, we can say that can we say that every boundary point is a limit point? Because if you will see, then you will realize that by looking that the boundary point is the limit point, but it may not be true. So let us see what is the statement. So the question is every boundary point a limit point? So here is we have the answer, no. A boundary point may not be a limit point. Okay, how we can see that? You can consider the set A consisting a singleton set 0, okay, which is a subset of R with the usual metric. Then A has no limit point. Okay, A has no limit point, but the boundary of A is the singleton set 0. Okay, so you can see that A has no limit point, but the boundary of A is equal to 0. So the boundary point may not be a limit point. The next one is that prove that a boundary point of A, X is a boundary point of A if and only if for every epsilon positive, the open ball as epsilon x contains points of A, okay, and the complement of A. So this is basically what? This is the definition of the boundary point, because X is the boundary point of A if and only for every epsilon the open ball contains point of A and the point of X minus A. So this is nothing but it is the definition, because the definition is that a point is called a boundary point if every open ball with center X intersects with A and its complement. So it contains point of A and complement of A. So this is by definition you will get, and other way you can get by using the other argument over here. Now we have some more exercises. So again, first exercise, now we have that let A be a non-empty subset of a metric space X. Then prove or answer the following statement. What are the statement? Statement is that interior of A intersection boundary of A is equal to empty. Okay, and interior of A union boundary of A is equal to closure of A. Okay, so this you can prove by taking the interior of A is the complement of closure of complement of A, while boundary is contained in the latter, and so the intersection is empty, and this way we can prove. So here is, this is your whole close, this is your the bar. So okay, the second is the boundary of A is empty if and only if A is both open and closed. Keep in mind, in the discrete metric space, every set is open as well as closed, and therefore the boundary of a set in a discrete metric space is empty by using this one. So here is, we can prove this, that if A is open, okay, then the complement of A is closed, and so it is equal to the closure of the complement of A. If A is closed, then the closure of A is equal to A, and therefore boundary of A is equal to closure of A intersection closure of boundary of A, which means that it is equal to A intersection complement of A, because A, this is equal to this one, and they are closed set, so it is equal to, but this is equal to empty, so this is equal to, therefore boundary of A is equal to empty. Now set the boundary of A is empty. Suppose the set boundary of A is empty if and only if the closure of A and the closure of complement of A are disjoint. Since the latter contains in complement of A, it follows that the closure of A and the complement of A are disjoint, and since their union is X, the closure of A must be contained in A, which implies that A is closed. If one reverses the role of A and complement of A in the preceding two sentences, it follows that the complement of A is also closed, and therefore A is both open and closed in X. So we have the statement which can say that the boundary of A is empty if and only if A is closed as well as open. Now the third statement is A is open if and only if boundary of A is equal to, you take the closure of A and remove the LA. Okay, then it is your boundary of A. So that you can follow from this remark, which says that boundary of A is equal to this thing. Okay, and if A is open, okay, so if A is open, then X minus A is closed, and so X minus A is equal to the is closure, and therefore boundary of A is equal to closure of A intersection complement of A, and this is equal to your closure of A minus A. And now since boundary of A is equal to boundary of its complement, and boundary of its complement is equal to the closure of A minus A, which is a subset of X minus A. So by part A we can say that X minus A union boundary of X minus B is equal to the closure of X minus A. Since both summand of the left hand side are contained in X in complement of A, it follows that the right side is contained in the complement of A, which means that this complement of A is closed in X. Okay, so complement of A is closed as, this means that A is open. Now next is if A is open, then A is equal to the interior of closure of A. So whether this is true or not. This is not true. Why? We can consider a set A which is equal to open interval -1 0 union 0 1. So this set is open, this set is open. So arbitrary union of open set is open. So this is finite union of this union of two open set is open. So A is open subset of R with the usual metric. Now what would be the closure of this? The closure of this is equal to close interval -1 to 1. Okay, -1 close interval -1 to 1. So the closure of A closure of A would be equal to minus 1 and 1. Now what is the interior of this? Closure of interior of this is equal to minus 1 and 1. So this is minus 1 and 1. However, we always see that A is a subset of the interior of closure of A, because A is the subset of this, and take the interior both the side, and because this is your open set, so this is equal to this one. So this is not true. The next exercise is let X is equal to R2 be a metric space with the usual metric. Okay, then A is equal to this one with the usual metric, and A is equal to this, B is equal to this, and so on. Now you find the boundary of A, B, C, D. What is the boundary of this? How will you find the boundary of this one? Let's see. The complement of A, the complement of this is this set. Okay, because here is y is equal to 0 where all the points x, y where y is not equal to 0. That is the complement of A. Now we claim that this set is open. Okay, this set is open, but if x, y in the complement of A, okay, then y should not be equal to 0, and the open sphere with center at x, y, okay, and with radius y, mod y, with center at this and radius mod y is contained in the complement of A, and therefore A is closed. But the closure of the complement of A is equal to R2, which means that every point of A is the limit point of the complement of A, and therefore the boundary of A is equal to A intersection R2, which is equal to A. So the boundary of this set is equal to A. So this way you can calculate. Now you see that you cannot use directly the definition of boundary of A. You will have to use some techniques to prove that, to find the boundary of A. In the same way, let us take the second example where B is the subset of R2 such that x is greater than 0 and y is not equal to 0. Okay, then what would be the closure of this set? The closure of this set is equal to x is greater than or equal to 0. Okay, including all y. And now the closure of this and this set is closed set. This set is your closed set, or you can say that this set is your open set. This set is open set or this set is closed set. Okay, but x minus b by the complement of b. Okay, this because b is your closed set, so it is equal to the complement of closure of b is same as the complement of b, because this is open in x, and therefore the boundary of b is equal to boundary of b minus b. So minus b, you can say that closure of A, so closure of A is this one, and remove b. So b is what? B is equal to, you have x is greater than 0 but y is not equal to 0. So you will get either x is equal to 0 or both x is greater than 0 and y is equal to 0. So this is the set, this is the boundary point of this set. Now let us find the boundary point of the set C. So C is equal to A union B. Okay, so this you can do by yourself. Let us move to the last one, E. E is this set. Okay, here is E is the set of all set, and here is x square minus y square is less than 1 and it is greater than 0. So what is the boundary of this set. So boundary of this set, again you find the complement of this one. So complement of this is this one. And the boundary of A is equal to closure of A in intersection the closure of the complement of A. So this is the complement of A, this is the closure of A, and now you can combine this one, you can take the intersection of this is equal to this set. So this way you can find the boundary of this set. Now finally let us take F, this last one. Here is the set of all points x, y in R2 such that x is not equal to 0 and y is less than or equal to 1 over x. So again find the closure of this set. So closure of this set is equal to set of all points x, y such that x is equal to 0 and y is less than or equal to 1 over x. And find the complement of this and its closure. The complement of this and its closure is this set. And then you can calculate the intersection of this and this which is equal to this set. And this way we can calculate the boundary of a set. And at the end we will see that some other questions related to these exercises. Okay, so I stop over here. Okay, and we will continue in the next talk. Thank you very much.